I showed you how to re-enable CCD cameras to go and view infrared, and a couple of people asked for me to elaborate on infrared LEDs and LEDs in general, so I'm going to come up with a fun little project. But first we have to cover some basics, okay? Infrared LEDs, or LEDs in general, an LED is a light-emitting diode. If you don't know what an LED is, look at the front of your computer, look at damn near every piece of electronics on the market nowadays. They have LEDs. They're just little lights. LEDs are low power and low current, however they have a greater amount of power output, unlike standard light bulbs. They're also a form of diode, hence the name light-emitting diode, which means you can't plug them in backwards. Now, unlike a resistor or motor or other passive components, you can't put more voltage and more current across an LED to make it brighter. It has a maximum breakdown, and once you reach that, it's just going to fry, pop, sizzle, or just generally not like you anymore. Now, to prevent this from happening, what you have to do to the LEDs, you have to put something called a current limiting resistor, or just a resistor, so it doesn't draw too much current off that LED. Now, if you miscalculate this and you put a resistor that's too great of a value, it'll draw too much current across that LED. But don't fret. LEDs usually have a very broad range of current and voltage. Example, some of the LEDs I'll be using in my infrared segment, or the infrared rifle segment, can go anywhere from 1.2 to 2.2 volts. So that's a whole volt. That's a lot in electronics. And it can also be powered by 20 milliamps to about 80 milliamps. So that's really broad right there. You don't have to worry too much. LEDs are very forgiving technology. Now, to calculate the resistor that you need, you have to know this formula, or one of many. Knowing Ohm's law would help a lot, but I know people are lazy, and Google pretty much will teach you everything. So I'm not going to get too much into this. Check the show notes. I'll give you some Google search terms and maybe some links and crap, maybe some formulas in the end. Depends how lazy I am. Okay, your resistor that you have to calculate your resistor. You got to know the voltage source of the LED. The voltage of the LED, and then the current of the LED. And the formula is the voltage source minus the voltage of the LED divided by the current of the LED will equal to the resistance that you need to put across it. There you go. You can also string the LEDs in series, you can string them in parallel, learn Ohm's law, and you'll be able to go and shift your math around a little bit. Don't want to get too complicated. And this is LEDs. Pretty simple. The second part of this is transistors. Now, transistors are a really nice technology. That's all of our technology today is based off of transistors, CPUs, logic, all that fun stuff. A transistor is an electrical component which allows you to control the flow of a greater amount of voltage and current with a smaller amount of voltage and current, like a valve. So, example, you can use a 3-volt power source to turn on a circuit that needs or is using, say, a 40-volt source. Okay, do you understand what I'm saying? I hope so. Otherwise, check the show notes. Now, there's two kinds of transistors. You have PNP and NPN. And the difference between the two is how they work. I'll put it in the show notes. Don't want to overcomplicate you. You're probably confused as it is. But the main thing is the direction of which the electrons flow. Now, you have a base, an emitter, and a collector. Okay? Now, when you trigger that base has something called a saturation point. Once you meet or exceed that saturation point to its tolerable limits, it'll allow the flow of electricity from a secondary circuit from either the emitter to the collector or the collector to the emitter, depending on the type of transistor it is, whether it's NPN or PNP. Now, determining on the schematic symbol will determine what it is, NPN or PNP. But you're probably saying NPN, PNP, PNP, well, this is confusing. Give me an easy way of remembering all this crap. So, NPN, not pointing in. And if you look at the schematic symbol, it looks similar like a diode. So that shows you the direction of where the electrons will flow. PNP, or pointing in proudly, is the opposite direction. So just by looking at the schematic, you can understand that once the base is triggered, in which direction the electrons will flow. Now, let's get into some fun design. Now, this is just lecture, folks. I'm not going to go and show you all the soldering and whatnot. What I did was, knowing what I know about LEDs, I created a 30 LED array. So I have 3 LEDs in series, and they're all lined up in a 10 row, or column, 10 column parallel mobobber. This thing was a pain in the ass to build, even for me, because it's relatively close quarters, it's compact, shit can go horribly wrong really quick. if you really do want to make this infrared LED array, which can be used as an infrared floodlight in your infrared vision that we did in the previous episode, you can have a ghetto-tastic night vision, which I'll show you in a little bit. Now, if I power this thing up, I've designed all of these. It doesn't look all too impressive without the night vision on or in daylight, but you get the idea. What this is going to do is it's just going to fill an entire room up with infrared light. Using this thing with infrared vision, no joke, it's like clear daylight. It's pretty cool. You don't need to use 30 LEDs. You can use 3, you can use 2, you can use 10. Do the math, do the calculations, hit Google, type in LED calculator. They got, like, you know, Java applications that'll design the entire array for you in either schematic, ASCII, or like how to actually wire it up, like actual pictures of LEDs, resistors, and batteries. Now, what we know about transistors. A transistor can use a small amount of electricity to trigger a larger amount of electricity. So you can use a general purpose small switching transistor, like the 2N3904, or a slightly more powerful transistor, like the 2N3055, to take an infrared source, like an infrared remote control, and you get something called an infrared phototransistor. It looks just like a clear LED, but what it really is it's a transistor that its base is connected to a photosensor that detects infrared light. So the more infrared light that hits it, the more electrons it lets through. So, and I'm sorry, but that's something I forgot to mention about transistors. If you don't meet the saturation point, it'll only allow a small flow, not the full flow of electrons. I'm sorry, I forgot. Derf. Anyway, you have your infrared phototransistor, which is a detector of infrared light, hooked up to a battery pack, so you can actually trigger a secondary larger power transistor, which I'll put the schematic online, or maybe I'll do a schematic on the screen somewhere. And essentially, you can use your remote control to trigger a transistor, which then triggers an infrared array, which now, instead of having one rinky-dink 20 milliamp, no, I think it's 20 milliwatt, 20 milliamp, whatever, rinky-dink piece of shit infrared LED, can now power, trigger a massive array, essentially giving you greater range. And then a little bit later, I'll show you my infrared rifle, which is just using regular magnifying lens and some crap household junk. You can piece together a way of actually focusing this infrared beam for longer range. Let me explain how I designed my infrared rifle. The basic rifle is going to be nothing more than a lens and an LED. The lens you can get from any El Cheapo magnifying glass. I actually got a 2-pack of magnifying glasses for $1 at my local, El Cheapo shops. We call them dollar stores around here. Then what I did was I cut 2 rings out of 3-inch PVC pipe. That's what this is, 3-inch PVC. You can get the PVC pipe at any plumbing store. It's not horribly expensive. And what I did was, I know a little bit about PVC. What I did was I cut a small chunk out of the edge of 2 pieces. And then I took them and I wrapped zip ties around it so it kind of clamped shut. I threw it in a pot of boiling water for a couple of seconds and it essentially shrunk it. Then I glued one in here, and then the other one I left slightly bigger so it would just lock in. And that's pretty much it. Just, if you want to make it permanent, you can glue it in, but I like to use my parts over and over again. So we got a piece of 3-inch PVC pipe, a 3-inch to 2-inch reducer, and then a piece of 2-inch. Now what this does is it allows, I sanded the inside of this reducer down on the inside so this 2-inch can slide inside the 3-inch. There you go. Now, to keep the inside pipe over here right by the array from bouncing around too much, I got some foam, just packing foam. I think I got this from when I got my laptop in the mail. And I put it around the 2-inch piece of PVC, just a couple of segments. I cut them up, and then I just taped them on. That way it's some kind of soft, squishy support so the inside doesn't bounce around horribly. And then I pretty much just electrical taped the infrared LED array right to the pipe, ran the wire out, around, electrical tape, the power supply for the infrared array, taped on the power supply for the driver circuit, and here's the driver. And for the detector, if I can get it, the detector over here, I just took a piece of El Cheapo, pen, cut a small tube out of it. That way, when I have a remote control, like this is my camera remote right here, the LED is actually exposed itself. So what I can do is I can just match these up, just like that. That way, there's no ambient infrared light coming from the sun or other third-party sources, like another remote, that will that'll do a false trigger on the rifle. I also take little chunks of this, foam stuff, and what I'll do is I'll actually tape it straight to the top, just a small chunk, so I can get the appropriate height that I need to match up with the remote control. Then I'll just tape the remote control to the top, drop the remote, and hopefully it didn't break. Use my thumb to operate the buttons, like so, and then use this arm to focus. That's pretty much an infrared rifle. If you don't want to go and use PVC pipe, and you're really cheap, or you just can't get any, you can go and get a plastic soda bottle, or a couple of them, and just regular packing tape, and make a couple of tubes the same way, just like this. It's really not too difficult. You can also use sheet metal. I mean, you can even use oak tag. I mean, you can use old cereal boxes. You don't have to use a 90mm lens, but if you Google, focal point mathematics and all that crap, you can go and figure out what lens would be most appropriate for your project. I have 3/4 inch lenses that don't go as far, but do just as good of a job. So, there you go. I've got my infrared array powered up and focused towards the wall next to me, because if I put it directly in front of me or pointing towards the wall behind, the camera loses focus way too easily. So I mean, here's, you can see the array on and going. The array is pretty powerful. I wasn't kidding when I said using this array with infrared vision, you could quite literally light an entire room up clear as day. Wasn't kidding whatsoever. So what I'll do now is I'll go outside and I'll go downrange a little bit using the infrared rifle and control the zoom to my camera, just to show you that with the infrared array and photo transistor and possibly an even more powerful transistor, you can control infrared devices from a greater range using a focused beam of infrared light.